cloud.
You've opened the waiting room.
I will now let everyone
still
in.
Aren't we still in the private one?
Are you letting folks in, Nancy? Is that what you said?
Yeah.
Okay.
That's somebody that's on here
Can you
twice.
just open the waiting room?
Yeah, there's an admit all button, so you can just do it all. What were you saying? Somebody what?
I was just saying, I thought this was still the private room, then that we had to leave this room and transition over to the other one, but I could be wrong.
Oh, no,
it's
this
all
is
this one
your
room.
panel.
It's all one room.
Yeah, just open it and let's begin because it's already.
That's what I did.
Yeah.
And I'm going to, change it to speaker. Okay, we're ready to go. Welcome everybody to the science panel. This is Atlantis Grail Stadium at SPC headquarters up in space. And it's Into the Quantum Blue, Astrophysics and Mind-Blowing Science. I would like to welcome all of our guests. We have, of course, Vera. We have Bridget Landry with Jet Propulsion Laboratories, Michelle Thaller with NASA, Dr. Michelle Thaller, and Dr. Jeremy Frank with NASA. We are going to ask all sorts of sciencey questions. Don't you like my word, sciencey? And
technical term.
Find out all the answers from our experts. Ready to go.
There we go.
All right. In the Atlantis Grail series, there are many examples and notions of reality boundaries. For example, the quantum stream, which is a containment state for the fleet of the Armada ships, both in stationary and in ultra fast motion. What was that term that super duper fast or something like that?
Is that from Spaceballs?
Spaceballs, I'm thinking, yeah, ludicrous
Yes, ludicrous.
Yes.
And the quantum shield, which is a stationary, which contains and holds the ghost moons in its own reality, a mini universe of its own, and the hardened dimensional sphere bubbles that contain the Pegasi aliens. So I'm going to ask if you guys can enlighten me on cosmic membranes, something that separates the universes or states of matter. Is it altered space-time? Is it a black hole firewall, string theory, frequencies? You tell me, because I am totally unsciency.
This is fun.
Just how many terms can you throw at us at once there?
Well, of course, I'm going to go as many as I can, Michelle.
Which one do you want to talk about? You want to talk about the definition of a membrane?
Yes.
Okay. All right. So I guess I could probably take a hack at this if that's okay with you.
Go for it. Yes.
Okay. Well, yeah. So, I mean, this was an idea that came out of, it basically came out of string theory. And it has this idea that, people always, string theory is the idea that every elementary particle that exists is basically defined as a vibration of the same thing, as some kind of string. And these things are incredibly tiny, much, much smaller than subatomic particles. And the interesting thing is scientists will get a little cagey if you ask them a string of what? Are we talking about like a string of energy, a string of what? And so the idea was basically that it's hard to say. It's a vibration of whatever the universe is made out of, space and time. And this kind of evolved into the idea that, instead of like thinking about a one-dimensional string vibrating, you're thinking about sort of a drum head. Think about a two-dimensional drum. When you strike it, it makes all kinds of vibrations going out in many different directions. And, people have successfully modeled pretty much the behavior of every elementary particle so far as this membrane that vibrates. And this basically represents the space-time of our universe. So like in this model, you're sort of thinking about a two-dimensional drumhead vibrating. How many dimensions are there? This is open to a lot of interpretation. In order to get the math work, if you're Brian Greene, for example, he's one of the people that really writes about this, one of the particle physicists. He actually needs this membrane to actually be able to move in 11 dimensions. So in order
11 dimensions. Yes, I've heard of that.
That's
the
right.
11
Yeah.
dimensions.
Yeah, that's right. But the idea is, I mean, I give guest workshops at CERN in Switzerland. The large European particle accelerator, the Large Hadron Collider, is the largest particle accelerator in the world, at least at this point. And one of the things that I keep trying to tell people is you are not leaving this room thinking that elementary particles are little balls. You're not. They're not. I mean, the idea that an electron or a proton or a quark are little balls. I mean, it's an easy way to think of them, but they're not. And really what, an electron is a vibration of what we call the underlying membrane, space-time. And then the interesting thing is that could there be, if you think about just as a model, a two-dimensional membrane, could there be stacked in a third dimension, other membranes, other universes? And the big intriguing thing right now is that when you do the string theory, all of the forces of nature that we're familiar with, things like electromagnetism, all of the nuclear forces that hold atoms together, all of those actually stay bounded on the surface of this membrane, however many dimensions it is. Interestingly enough, gravity does not. Gravity is the one force that may actually have the ability to vibrate other strings, other membranes with it. And so gravity might actually have the capability. So one of the reasons they like this mathematically, and I'll wrap this up quickly, is that if you do the math, all of the forces seem to act very similarly. Electromagnetism, we resolved into one force. The nuclear forces, we've resolved into sort of the same force on different scales. Gravity was always the outlier, didn't work. But if you let gravity leak into 11 dimensions and vibrate these different ways, it ends up acting just like the other forces, like electromagnetism and everything else. So, interesting, we don't know what dark matter is. We have no idea. But one idea, something that has mass, but nothing else, just mass. You can't touch it, you can't smell it, it's not there, it just has mass. Some people think that's actually gravity from other universes. I mean, it's a lovely, intriguing idea. We don't know.
Oh my God, that is mind-blowing.
That's right. But so I will say,
Definitely.
I'll just in closing, these ideas are really wonderful. You can read about them. Like I said, Brian Greene has written some very good books about them. They are now becoming a little bit superseded, and we can talk about this again, in another question, by something called the holographic universe. So I'll leave my definition of membranes there. But basically, our membrane is however many dimensions our universe has, and in many directions it vibrates to actually sort of make every elementary particle that exists. There's no such thing as there's only one electron in the universe, right? There's a vibration that means an electron. And whether that vibration is happening here or billions of light years away, it's really all the same kind of vibrating thing.
It's stunning. This is just amazing stuff. And one thing that I've never gotten was string theory. It's like,
I mean, anybody else want to take what is a membrane?
Out of my wheelhouse.
Okay, I got it.
Altered
Me too.
time?
Okay, if you guys want to talk about bending, I mean, one of the things I can do, I noticed, is I can share my screen. I have a new video that we produced last week that is about some of the space-time bending we're seeing around neutron stars. And
wow.
Neutron stars are the dead cores of stars after they explode in a supernova. And these things are only, the one we're studying is about 16 miles across. And we can actually see space and time bending around it. We can see the back as well as the front as we look at it.
wow.
So something is right in front of your eyes, basically, and you can see behind it because space and time are bending around it. So cool.
Oh my God.
What's
Like a
the mass
black
of it?
hole a little bit. Isn't that like a little?
It's very much like a black hole, but not quite a black hole. Yeah.
Right.
What's the mass of it?
The mass is this is interesting. This is the most massive neutron star that we've ever known. And it's about 2.4 times the mass of the sun. And so you have all of that mass within a 16-mile diameter. And that's why you get lots of space-time bending around it.
Wow.
That is mind blowing. I mean, all these, like, once you get to these sizes and dimensions, it's like you can't even fathom this.
Oh yeah, yeah. Like I said, later on, if you'd like me to play the video, it's about 4 minutes long. I can do that.
Yeah.
But we can save that for another time. but
Right.
just whatever you like.
This is amazing. Oh my goodness. So the whole idea of like separating universes, it's like these membranes is just whatever their vibrational, like you said, the drum effect on the surface is just kind of, that's what keeps things apart. Or
That's
maybe the
basically
rest.
what we know about reality. That
Yeah.
what we
Yeah.
think of as reality, as mass, as particles, as everything, are
Right.
are vibrations on this membrane. Yeah, and like I said, I mean, I think that was very popular for a while. Now things, black holes have basically thrown a monkey wrench into everything in physics. And I mean, I heard you mention black hole firewall, and we're all like, so we're trying to figure out how you solve the black hole problem right now, and that may lead to new physics beyond this idea of a membrane.
Can I ask a question about those, the layered membranes?
Mhm.
Do you get induced resonance like you do with sound?
Well, so this is, this is the thing. I mean, the answer is, quite honestly, we don't know. And, do the membranes overlap? Do they interact at all? Some people are wondering if, something like a big bang, some sort of big change, some energy into the universe could be when two of them touch or something. There's lots of people that are modeling that sort of thing. So the simple answer is, we just don't know. If gravity does manage to flow between membranes, then I would think there would be something like that. But but that's just a guess on my part.
Wow. This whole thing is just so mind blowing.
Oh yeah. I mean, there's a lot of good stuff about this. So, like I said, some of the people that are writing about it that I think write about it quite well are Sean Carroll, who's at Caltech, and Brian Greene is at Columbia. I think they are both very good sort of public level writers about this stuff. I mean, you can find if you go to some good sources like scientificamerican.com and things like that, you can find out. I remember the New York Times did a big 2-page spread last year or 2 years ago on the black hole paradox and stuff.
Right.
So that's all going to become very interesting. There's a big move now to try to define, Isaac Newton could describe pretty well how gravity moves things, and then Einstein came up with this why, that there was an underlying space-time that bends, and that's why things have orbits like that. But now the question is, what is space-time? What is this stuff that Einstein called space-time? And that is causing some really interesting problems in physics, because black holes, where the gravity is so intense, it basically crushes space and time out of existence. The physics of black holes may be giving us a glimpse of the underlying structure of the universe. So take what we think of as space and time, collapse them out of there. What's left? And it actually may be something that's pure information. And this is what we call the holographic principle. The physics of black holes stopped working a while ago. Stephen Hawking knew there was a real problem, because the universe shouldn't be able to just simply give up information. When something falls into a black hole, what was its charge? How fast was it spinning? I mean, we know how massive it was, because the black hole contains the mass, that the event horizon, the curvature of space, the point of no return moves out as the black hole gains mass. But everything else seems to be lost. Information goes in and never comes out. And the universe just doesn't seem to do that. It doesn't match the conservation of energy, and so this idea now is that, with space and time gone, it turns out that space and time weren't really real at all. They were just kind of emergent properties, almost sort of a projection of an underlying, perhaps even two-dimensional reality and information structure. And this is called the holographic principle. Now, the holographic principle doesn't mean that anybody made a hologram. It doesn't mean we're in a computer simulation and somebody's manipulating us. It just means that our universe may store information the same way a hologram, a similar way. A hologram is a two-dimensional thing, but if you look into it, you see 3 dimensions. I've even been to a hologram museum in Copenhagen, where you walk around the hologram and you see it move, because you're seeing it at different directions. There's somebody in there waving to you. And all of that information is actually stored on a 2-dimensional surface. So the idea of any change at all, any motion, is actually an illusion. Space and time itself are an illusion, a projection of this underlying information of the universe. And that's your 25-second description of the new holographic principle, which is gaining a lot of traction in physics right now.
That's something to check for the Google.
Right.
Yeah.
Did you do some
I have a
Googling on it?
question
Yeah.
about that. If we can continue lingering on this for a bit. So in mathematics, the information theory basically says that the amount of information in a string is, the the sum of the probabilities of the strings, or the negative log of the probability of the strings. So in order to talk about information mathematically, I need symbols and I need frequency of occurrence of symbols in some larger set of symbols. So Michelle, if what you're saying is that there is some underlying, let's call it, set of symbols or set of things, and some probability of those things occur, and that is preserved, then at some point someone's going to have to tell me, the dumb mathematician, what are these things? What is the set of things that defines the probability of the things being there, so that I can talk about information that way? Does anybody have any idea what those things are and how we talk about their likelihood of existing and why they are or are not conserved in any
Yeah, I
meaningful
mean,
way?
so this is where, this is now beyond my wheelhouse, as you'd say, but I would think that someone like Sean Carroll would know. I mean, Sean Carroll has done the mathematics, the underlying mathematics of the holographic principle. It started, I mean, the idea started a while ago with a man called Leonard Susskind. He was one of the founders of this. I actually interviewed him for NPR about 2 years ago when he was sort of getting this holographic principle together. I think there's a number of videos on YouTube of Leonard Susskind discussing sort of the general principle of the holographic universe. But as far as exactly what a mathematician would want to know, I mean, I'm sure there are all kinds of academic articles on the mathematics of this, but this is where I, as an astrophysicist, I did a lot of math, but not that much math.
Well, I know.
I got totally lost after the first couple of sentences.
Oh, I'm sorry. Yeah, well, the holographic principle.
Okay,
Yeah, that's a weird one. Yeah.
I am probably the most unsciency person you will ever meet. I was very good in math, and you're supposed to be good in both, but
Well, I mean, if you're curious and you know how to ask a question,
Alright.
and and you're
And
curious as to
that's-
what the answer is, then you're as sciencey as they get, as far as I'm concerned.
I wanted to quickly just interrupt. This is something that Michelle mentioned last year,
Oh,
and
yeah,
I got this book. So this is pretty good. I haven't read the whole thing yet. I'm just skimming it right now, but it's really great. I mean, it's kind of like a beginner's thing. Like if you just don't know anything, just pick it up. And this has been good. And the other thing I just got recently is this book. It's the God equation, which I think again is sort of like the theory of everything. I just got this book, so I haven't really read it at all. But so these my two recommendations that coming from somebody who's completely clueless in general.
even better than I do. I mean, I'm totally clueless, but then I'm good at math. So
So should we move on to,
Yeah. Sorry.
no, I was just gonna say, so should we move on to question number 2?
Sure.
I think so.
Yes.
All right. So Nancy and I were going to take turns asking. So here's mine. So there are 4 known fundamental, God, can't talk today, forces in physics. So we've got gravity, electromagnetism, a strong nuclear force, and a weak nuclear force. What are the current contenders for a 5th force of nature? Could it be dark energy?
Possibly, yeah. I mean, so when I say words dark matter and dark energy, I'm telling you pretty much all we know about those things. I mean, honestly, what we know about them is basically nothing. The theorists certainly are working on dark energy, and they're wondering if it could be some sort of negative form of gravity, which would count as as this as a 5th force, or maybe something else. I need to read more about it, but I know that at Fermilab in Illinois in the last 6 months, they've been doing some very interesting experiments about how specific particles decay. And they seem to be diverging from the 4 fundamental forces model. So there are some particle accelerator experiments that are also kind of hinting that there may be some other forces that we're unaware of at this point. The the thing about the forces, as you know, is that they're vastly different in their strength. So, I mean, the strongest strong force, it actually keeps like, the nucleus of atoms together. It's hard to imagine ripping apart, a nucleus of an atom. And then of course you've got, the weak nuclear force, which actually holds neutrons together and things like that. But gravity is, I mean, I should look this up, but gravity is many thousands of times, or maybe even more times weaker than any of that. I always tell people, it's like what gravity would like to do is rip particles from my arm and accelerate them to the core of the earth, right? Because that's where gravity is pulling them. But that's not happening because the nuclear forces and the chemical forces in my hand are much stronger than gravity. So this dark force, this possible dark energy, it only seemed to show up relatively recently. It was probably there all the time. But the universe was so dense, we didn't notice it. There seemed to be a crossover about 5 billion years ago. The expansion of the universe changed. And this is something that we're building a new mission at NASA. The first major space telescope named after a woman, Nancy Grace Roman.
Cool.
The Nancy Grace Roman was the first director of astrophysics. I met her before she passed a few years ago. And she was the first director of astrophysics at NASA in 1958. Think about that. When, in 1958, she was the head scientist, the head astrophysicist at NASA. And she was the one who was really the mother of the Hubble Space Telescope and all these space telescope ideas. But we noticed through Hubble, and now we're continuing with Roman, which will launch in the next 5 years. Until about 5 billion years ago, the universe was expanding, but the rate of expansion was getting a little bit slower. It actually was slowing down a little bit. There's all this dark matter, there's all this gravity, there's all this stuff sticking stuff together. But then there was basically a point in time where the universe reached a critical density, that the gravity, the attractive force of gravity started to be overcome by this underlying, perhaps, fifth force of anti-gravity. Now, again, this is conjecture. We don't know if this force exists yet, but we're building $1 billion spacecraft to help us find out. So this is important to us. And so the question is, has the expansion of the universe done this many times? Have there been different eras that were actually sort of dominated by different forces? So 5 billion years ago, the universe started to accelerate. The rate changed again. So the rate went from expanding but slowing down to expanding but speeding up. And like I said, this was only discovered in 2011. So this is really new. Nobody expected the result. The result was two really good friends of mine from graduate school. Always makes you feel like a real schlub when two of your friends get the Nobel Prize. But so Brian Schmidt and Adam Rees were two friends of mine from grad school. But they shared the Nobel Prize with Saul Perlmutter for this. And nobody expected this. They were all trying to measure that slowing down. We expected the universe to slow down over time because of all the gravity. And instead we find it's accelerating. It's like, who ordered that, right? I mean, nobody expected that. And so now we need to figure out why the hell the universe is ripping apart, because we did not predict that.
Yeah, that's because doesn't that change the idea of the slow, cold death of the universe before the idea that everything just goes to zero? And
well,
then,
the question, yeah, it might. Yeah, that's right. It probably will affect the end of the universe. And, we don't really understand how. I mean, there's some conjecture. I mean, certainly now it looks like the universe is not going to collapse gravitationally again. Right. There may actually still be an oscillation, a new universe kicked off. And I can talk about that if you like. But basically, the idea is this expansion could make things much, much colder. everything flies apart. And so, it's the sort of thing that, there may actually be so much acceleration that relatively sooner, there'll be nothing else in the sky except our Milky Way galaxy. And could this force become so dominant that it starts to rip apart that? Could the stars start to fly off from the galaxy? Could it even become so strong? And again, we don't know this, but could it become strong enough to rip apart matter? Could there be a day when this underlying force of the acceleration of the universe literally does send the electrons spinning away from the atom, the nuclei, and all matter just goes poof? So
Wow.
that's called the big rip, and we don't know that.
That is terrifying.
But certainly the idea that the universe has this extra component of acceleration is getting hard to deny now.
Oh my God. Yeah, that always, the question was, I always hope for the cyclical thing, like where the idea is that there is, like you said, another universe just kind of is generated or picked up or however, it's.
Well, there very well may be. And in this, if you want to, there's a number of podcasts that I think are done by, oh God, it's not by Martin Rees, it's by another famous English astronomer, but there are a number of people who thought of this. There may actually be another cycle of the universe set off, but not in terms of gravity collapsing, but in terms of entropy. And then this is very interesting. So let me put it in this way. The weirdest thing about light that I know about, and I don't think people spend near enough attention to this, it's people are starting to really delve down into this, is that light itself does not experience space or time. If you are going at the speed of light, you're probably familiar that as you go closer and closer to the speed of light, time to you from an outside observer seems to be slowing down. You seem to be going slower and slower. When you're at the speed of light itself, time stops by definition. And that means that a photon doesn't experience any travel time either. All points in the universe are one. It takes 0 time to travel anywhere in the universe. So the universe to a photon is basically a singularity. It's a single point. Now, in a very, very far future where everything has expanded, and black holes themselves, probably the last remaining matter, begin to actually give up their energy and radiate away in what we call Hawking radiation. The last thing you're left with is a whole universe full of very low wavelength, low energy light. Now, as vast as the universe has expanded over the trillions and trillions and trillions of years this would take, bigger numbers than that, this huge universe now has nothing but light in it. Light doesn't experience space or time. So what's the size of this universe?
Oh my God.
This vast, vast universe effectively becomes a singularity, a pre-Big Bang state. So we may be in a cycle. What did things look like before the Big Bang? This. It could be that the universe has this cyclical nature that when you go all the way back to photons, there's no way to tell time or space anymore, and you're basically a singularity. And maybe that sets off a new Big Bang.
Boom.
Time is sort of a human concept anyway.
Oh yeah, well, we're sure that time isn't the way we perceive it. I mean, our physics wouldn't work if that were the case. But but the idea that what is time itself, space and time. So I mean, seeing as we're just having fun blowing minds, the big thing they're looking at right now is you've heard about quantum entanglement, that things in the universe can react basically instantaneously.
Right.
If you take two entangled particles, and we've done this to the space station, we've done this over hundreds of miles, it works every time. This is an experimental laboratory fact. If you have two entangled particles, will actually interact like if you flip the direction of the spin of one, the other one will immediately flip. And it's not a light travel time thing. They flip immediately. And that's basically because no information had to travel. The universe thinks of these two separate things. We see separate in space and time. The universe thinks they're the same thing. They're the same quantum system. And so now there's this idea that what we perceive as distance in time and space. So things that are either in the past or the future, or things that are either here or billions of light years away. The difference.
You guys going out to the park or something?
Like somebody's microphone on?
Somebody's microphone on.
Yeah.
You and you mom and Melissa.
Well, anyway, this idea of distance in either space or time is just the way that for some reason we perceive degrees of entanglement. We're more entangled to things closer to us, less entangled to things farther away in space and time. But there's no such thing as space and time really, in an underlying real sense. They're basically just a perception of entanglement.
Yeah, somebody who has got a microphone on, please turn it off or something. We're getting interference here.
Everyone check your microphone. Yeah, so the idea now is that, what is space and time? What is it? It may be that it doesn't exist at all. It's basically the degrees of entanglement that for some reason, whatever our brains are, interpret that way. It's I know I was here last year. I mean, the thing that's, I don't know if I talked about you last year, but I think a lot of people out there know that my husband died this year. And, I have this great tattoo in Elvish now. He wrote a goodbye letter for me that goes all around my body.
That's beautiful.
Yeah, it's his calligraphy, actually.
Wow.
And I mean, it's not that this helps the human primate grief of mourning. I mean, I still do plenty of that. Oh, there goes my roommate. But he exists just as much as he ever did. It's not that we're ever going to meet again in an afterlife,
Right.
but I'm still with him in what I think of as the past. But, I've also been dead for millions of years. Why be scared of death when, that's already what you are? I haven't been born yet. All of the universe, all of the universe exists as a thing. and degrees of entanglement in space and time, or how we perceive space and time, but that's not really what the underlying reality is.
Right. It's just, I think for us humans, it's really hard to like even grasp a lot of this because, but the
It's
idea of
impossible because
everything-
we can't think in 11
Yeah.
dimensions. I mean, no one can.
Exactly.
It's like, I certainly can't. All of this stuff though, I mean, it's fun to talk about in a mind-blowing way, but you have to realize it's based on experimental fact. The idea that light, you can't add the velocity, right? Everybody sees the speed of light at the same speed. You're going 90% the speed of light, you turn on your flashlight, what do you see? You see the light leaving at the speed of light.
Right.
That is an observational fact that was established in the late 1880s by Michelson and Morley at Mount Wilson Observatory in California. This is something that we know. And when that fact exists, that you cannot add velocities in time, everything else falls into place. All this weird stuff comes out of that. There's a reason. It's not just people pulling like all kinds of crazy stuff out of their minds saying, oh, look at this. I mean, there's an underlying reason for thinking these things. Some of it is still conjecture. We're still trying to find proof of membranes and multiple universes and all of that, but they all come from an experimental fact that wouldn't go away.
It's just mind blowing. Well, this is the question about, I mean, how does everything begin? How does everything end? Is there a pattern? This is just, a lot of times I think of, the idea of physics is just so much, people think of it as divine, but it's just basically digging deep into how everything works. I mean, it's just, that's how the world is, just like looking at the facts and
it all comes down. I mean, this stuff does come from the basis of experimentation.
right.
How quantum mechanics, as weird as it is, it works. Albert Einstein, I mean, so when we observe these neutron stars, this one we were observing was, I don't know, like 6,000 light years away.
Right.
It behaves as if space is bending around it according to Albert Einstein's equations. I mean, 100 years ago, these people got things really, really right. And I'm sure there will be corrections to it. I'm sure we will have different physics. But I mean, space and time went away 100 years ago in physics as absolutes. And now, and that was experimental. That wasn't just people's ideas. That was how the universe around us really does seem to function.
Right. Oh my goodness. What was the next question, you guys? Let's see. Did we lose our moderators?
The next part of that was in the Atlantis Grill universe, there's the idea of will and intent is a fundamental driving force, which is what gives Gwen the ability to work with starlight. Kind of think of it as a ultra focused free will, or the ability of an individual entity to make a choice. Could that possibly also be a fifth force?
I think that was part of that question, actually.
Yeah, it was.
Yeah, there was just the idea that I think my question was for this, whether or not any particle, as I say, entity, but it's just a particle, does its intent or like have any of it, could it be a force of nature? In other words, could its choice or the idea of it makes a choice to either move this way or that way be a part of that process? Just a thought. So, anyway.
Well, I've been talking for a long time. Anybody else want to answer that one?
Yeah. Or we could go to the next one. Like I said, this was a part of that.
All right. Realistically, okay, I think this is going to be in Bridget's. Realistically, how far are we away from establishing working bases on the moon and Mars? And what would we need before we could make it happen?
Yeah, that's there's reality and there's politics, and to be
or
fair,
are they already there and we just don't know about them?
No,
I wish that
trust
were
me,
true. Yeah.
I would know.
Oh, okay.
We'd know.
We'd know. Somebody on Reddit would squeal. I think realistically, in terms of what our science and engineering is capable of, I think we're farther away than I'd like to be. The loss of a large booster has really crippled our ability to do that kind of work. And the other thing is, there are a couple of ways we could do this. And the one thing I really worry about is that we'll send a manned mission, a crewed mission to Mars, and do it the same way we did with the moon, and go plant the flag and come back and never go again. And
yeah, that's not good. We don't want that.
So I would rather see it take longer and do it in a more sustainable way. You know, build a base on the moon, or a larger space station, or whatever, and do it in stages. Much as I love Heinlein and grew up on it, single stage to orbit, you know, all the way to the moon, it's unrealistic. Same thing for Mars. I think it's possible that we could get there by 2050. They're talking about sooner than that, but I'm not optimistic that would happen. Now, to be fair, I'm not that up on crewed missions. I do robotic missions, but we've become a little more cautious and a little less daring. In the 60s and the 70s, we were, I mean, yes, it was all spurred by, we got to beat the Russians, but we were taking risks that I don't know that we would be willing to take these days. And
what about if a private person, like a private industry, like Elon Musk got in on this thing? And
it's unrealistic. The amount of money, time, effort, support structure, it's unrealistic for it would have to not only be a government, it would have to be several governments. There just isn't the amount of effort involved is beyond. Now I can see the commercialization of the Earth or surface to Earth orbit becoming commercialized, but beyond that, it's going to take a while. It's like satellites. Originally, the satellites were all done by governments, and then as that technology progressed, then it became part of the private sector. And I think the same thing is true in expanding beyond that. That once we get people in a commercial effort to Earth orbit, then the government will have that to bootstrap to get to the moon, to get to Mars. But it's not going to be a person, Elon Musk is amusing, but it's not going to happen. He's just not going to be able to do it.
So we're not going to have a Tesla spinning around Mars orbit.
Well, if he does manage to get a mission out there, it could be very damaging. If anything went wrong, that would lower our tolerance to risk even further.
Oh.
And there's an analogy to the early days of flight. Anybody and his brother was putting together an airline, and there were no regulations on how they would run, and people died, and so it got this undeserved reputation for danger. And until the government stepped in and made regulations to even it out a little bit and to make it safer, so I believe the same thing is going to happen with space.
What about leapfrogging? For what I mean by that is, you put one station up in this orbit, then you take and you put something that's halfway between here and Mars. Then you put something even closer, kind of like a bunch of things. You
Yeah.
can't.
Unfortunately, it doesn't work that way.
Right.
There's this common perception that if you go to the moon, you can stage from the moon to Mars. And it actually turns out that in terms of the energy budget, it's cheaper to go directly to Mars than it is to go to the moon and then from the moon to Mars. And the idea of putting anything quote unquote halfway, basically you need a planet. And well, we don't know how to build a planet yet, so that doesn't work either. At least I don't know anybody who knows how to build a planet, and I'd be concerned if somebody said that they knew that, either because they were insane or because they know how to build a planet, right? Either way, it's concerning. So
Exactly. Now, I will say that having staging in Earth orbit is realistic and required. You're not going to go straight from the surface of the Earth to Mars, but that stage is one stage, and then Earth orbit to Mars orbit is going to be another stage. There's nothing in between that buys you anything.
Right.
That is actually more or less what the Artemis program, the human spaceflight Artemis program, is intending to do for the moon. So they're going to build a thing that's, call it sort of a stripped down space station writ small, but it's going to be in a very, very peculiar orbit in the proximity of the moon. And the technical term for this is a nearly rectilinear halo orbit, which has a precise physical meaning that I don't understand completely, but there's some interesting properties of this orbit. So it's not stable, but it requires very, very low propellant budget in order to stay more or less in the same place. At least that's what people believe. It's almost always in sight of Earth, which means no communication blackouts. And it's also almost always in view of the sun, which means that you can use solar rays to more or less continuously provide energy and power.
Charge it, right.
And there are variations where, so if this is the moon, there are variations that either are very close to the lunar North Pole or very close to the lunar South Pole, which means that you have very, very good access to either the lunar North Pole or the South Pole. So why is that interesting? Because of the way that the moon is, and Michelle's going to whack me upside the head if I get the details wrong, so stand by. Because of the relative orbit of the moon and the Earth, what happens is that there are areas in either the North or the South Pole that are both permanently in the sun, which is good because it means you can put solar panels on the surface of the moon and get constant power.
Right.
And there are parts of the moon that are in permanent shadow. So why is permanent shadow really interesting? There are two very interesting reasons. So the first one is ice, water ice. Water ice can be a resource. We're not totally sure how to mine that water ice yet, but we're thinking about that. And if you can get the water ice, then you can extract oxygen from it, which means you don't need to take it with you. You can get hydrogen from it. Conceivably, you could manufacture fuel and do all kinds of useful and interesting things. So from a sustainability point of view, that's really interesting. On the other hand, the fact that those permanently shadowed regions are permanently shadowed means they have been stable, cold, for the entire lifetime of the moon. So they are scientifically super duper uber interesting from the perspective of solar system evolution. What is the moon? Where did the moon come from? There are people who think that it was a thing that crashed into the Earth and it sort of tore part of the Earth away with it. All kinds of interesting theories. So being able to do the geology and the planetary science at those places is also super interesting. So, so anyway, the idea is that then you could stage a thing to low Earth orbit, and then you could stage that thing to this lunar gateway, which is what we're calling it. And then you could go from gateway to the surface and back with moderate ease.
Wow, that's actually fascinating. The fact that you're talking about the stages of the moon and the way that it's
honestly, scientifically, I mean, he's absolutely right. I mean, and not just the formation of the moon, which is a big deal because, like he said, we think the moon was probably caused by a giant impact. But whatever the Earth has been through, the moon's been with us. And, one of the things that we found evidence on the moon was about 300 million years ago, we probably got too close in our orbit around the galaxy to a supernova. And both deep sea sediments on the Earth and lunar samples confirm that there would have been this radioactive debris coming out of the sky at that time. And, and so everything, the Earth has changed so much, but the moon hasn't, especially these very, very stable cold areas. The only problem right now with getting both water and resources, and there's another reason these craters are great, is you can hide from solar storms. If they're always in shadow, when the sun puts out a big belch of radiation, it'll just go right over them and you'll be safe from a solar storm. The only problem with this is that these are some of the coldest places ever recorded in the solar system. And while we have space telescopes that can exist in sort of the cold vacuum of space, they don't have many moving parts. We don't really have rovers or suits that people could survive or anything that works at these temperatures. These are really, really cold. And so that would require new technology. I mean, let's face it, going to the moon and Mars is a question. We have the technology for it, but the budget would be incredible. And do you want to spend all of our Earth's resources on this right now when we have things like climate change, which we should probably be a little bit more worried about? There's things like the big deal with the moon and Mars having bases is very simple: radiation. You and I are not really aware that we're contained in this beautiful magnetic field. The Earth has a molten metal core that generates a strong magnetic field. And when there's a blast of radiation from the sun, which happens, I should say high energy particles more than radiation. When there's a blast of particles from the sun, most of them just bounce around. They form the northern lights. It's all lovely, But if you're on the moon or if you're on Mars, you're exposed to that. Neither of these bodies have strong global magnetic fields. And there was a solar flare, I believe, in between Apollo. It was either in between Apollo 12 and 13 or 13 and 14. There was a solar flare that would have killed any astronauts up there. And we realized that we got lucky with Apollo. We sort of got them out to the moon and back just a couple days, and there was never a big solar flare or big solar event when they were up there. We don't have any way to protect them from that except things that take money to launch because they're heavy. I mean, you could protect
what about
them.
Water?
Exactly, right? So you could
like
protect
a water
them.
thing.
Exactly, you could protect them with water tanks all around them.
Yeah.
So you would need fairly big, meter-sized water tanks, big enough just to have an entire crew in there, perhaps for a day or two. We could build that, but it's heavy. That's expensive.
Oh,
What about using the dirt? I mean,
Yes,
just
yes. So
burrowing
the other thing-
underground.
All you
Yeah,
need to do.
that's being considered as a possibility too. Or the other thing is that there are these naturally occurring geological formations in addition to craters. Some of them are called skylights, some of them are called pits. Think of sort of an underground lava tube type thing that has sort of open space in there. The trouble with those is, well, okay, so go hide in a cave, astronauts? No, that's not going to work. So, and are they? Some of them are quite large, and so conceivably you could sort of drive a habitat in there or carry a habitat in there, but it's totally unprepared. Nobody knows what the insides of these things look like, and so nice hypotheses and everything else, but the radiation problem is a bad one. Unfortunately, it's not the only one. There are a lot of others, like your food supply, your water supply. There are various psychological questions about, can the crew actually survive alone for that long? I'll say one thing about the budget outlay question. We answered all those questions during the Apollo era, right? Everybody asked exactly the same questions. Why are we spending 2% of the GDP on Apollo? And so I feel like the answers are much the same. Yes, we have all these problems and we need to be spending money on them, but I don't feel like that precludes making an outlay on these human spaceflight exploration missions. But without question, Mars is the big lift, and anybody who tells you different is probably Elon Musk trying to sell you a Tesla.
I actually agree. I think going back to the moon would be wonderful. It would be expensive, but it'd be wonderful. I think that's very, very worth it. Mars, we just don't know how to do yet. We don't have the technology developed yet to do it. And like he was saying, for these solar storms, all you need to do is get about 10 feet below the ground, and you're fine. But that means you need to bring construction equipment, right, to give you a tunnel or use naturally occurring features. I mean, this is possible, but it's just, nobody has given us anything near the budget at NASA to really do that.
Curiously, Some Mars mission concepts that I've seen suggest that we wouldn't actually go to the surface of Mars, but we go to Phobos or
Phobos,
Deimos
yeah.
instead. And we
That's right.
basically just hide behind the
Oh,
sun
that's
and put
interesting.
ourselves on the right side of Phobos and just hang out there. And then we wouldn't deploy to the Mars surface, but you could send rovers down there and you could have the crew teleoperate them as a way of trying to protect yourself from the radiation. And that's fine once you actually get to Mars, but you have to survive the trip. And that's still not a solved problem, shall we say.
Yeah. That is fascinating. Oh my goodness. Because so if you were staying on one of the moons, would that be just like a temporary thing, or would that be an actual station built there before you go down to the surface, or like?
It depends on your design. I mean, you'd also need to look at the specific orbits, and you'd need to say, okay, so what part of Phobos do I want to be on in order to maximize my radiation protection? But you can do that, right? We know the orbits, we know how they rotate, we know how they precess, we know where they are relative to the sun, and so people have actually done some of those analyses. I don't know if any of them are public, but you could find yourself sort of the safest spot to be and be protected. But you'd still need to get there, right?
That's right.
No protection on your spacecraft until you get there. You still have to solve that problem.
All right. What was our next question, guys?
Sorry, I was on mute.
I think we're having.
So we wanted to talk about space junk. The Chinese rocket debris that recently fell in the Indian Ocean, but the next time it might not fall in the ocean and hurt nobody, rather. What safeguards can be developed to prevent space debris from falling onto the Earth and hitting populated areas?
Supposedly, there are international agreements that the spacefaring nations are supposed to hew to. They're supposed to think about where they're launching their vehicles. They're supposed to come up with disposal plans for vehicles that go into low Earth orbit. They're supposed to be tracking of the space junk, and the space junk can in fact be tracked up to a point. I can't recall exactly what the sort of minimum size of a piece of junk is, but it's actually pretty small. And NORAD, among others, maintain databases of where the stuff is. They issue warnings to various spacecraft saying, hey, your spacecraft is in danger of being hit by space junk. You should go do a maneuver now. This problem of new space junk has been a problem for a very, very, very long time. And the commercial spacefaring entities are moderately well aligned with this. The militaries of all nations, perhaps not quite so much. In terms of getting rid of this junk that's up there, this is also a problem people have been thinking about for a long time, and various companies and countries have thought of a lot of different very clever ways to do it. I recall reading within the last month or two that somebody was flying some sort of novel experiment to do this. But one thing that you can do, if you think of anything that's in orbit, right, its orbit is dictated by its mass. And so if you make it heavier, it will come back to Earth a little bit sooner, both because of atmospheric drag and also because of its increase in mass. So one clever idea that I heard about was you basically fly up to a piece of space junk and you spray it with water. And then the water freezes and it makes it heavier and bigger and it goes back to Earth. Well, that's fine if the big piece of junk that you know about is big enough that you can chase it down. If you're talking about a flake of paint or a bolt or a bracket or something like that, that's just going to be very difficult. So it's a real problem and it's getting worse.
Is it possible people will literally get hit on the surface with stuff? I mean, just stuff
So for a
falling
large-
that you can't track?
Yeah, so for a large vehicle like this Long March rocket that the Chinese lost and other rockets that other people have lost, if it's a big thing and it hasn't gotten very far up, or if it's so big that the atmosphere does not turn it into its subatomic particles by the time it re-enters, then it's a risk. But just as Michelle was saying, if you do the math, 75% of the Earth's surface is covered in water. So if your thing was in an arbitrary orbit, which they're not, then the chances of it hitting something that is land are already less than 1/4. The percentage of land area that is populated by people is also very small. So the numbers just keep going down and down and down. So strictly speaking, is it a risk? Yes. Is it a big risk for something that's actually made its way into orbit? No. For a thing that's failing on launch, though, that's a completely different matter. This is why there is the existence of something called the range safety officer at every single launch site. It is the responsibility of the range safety officer to make sure that the trajectory of a rocket on launch is not going over anything populated. You keep airplanes out of the airspace, you keep boats out of the ocean. So really, launch and landing are the two biggest challenges for safety. An arbitrary thing falling on your head, not so much.
That's wonderful. I didn't know about the idea of the launch specialist for the person who keeps track of it. That's interesting. Yeah. No one. Yet another little detail I've never had considered.
So here's a little anecdote. So NASA's next manned spacecraft is called Orion. It's being built by Lockheed Martin. It's going to launch on SLS, and we all hope it works. The first test of the Orion was in December of 2014. I was fortunate enough to be observing that. And the first day that they tried to do the launch, they had a number of problems. And one of the problems was some Yahoo in a boat penetrated the range in Florida. And so that was one of several reasons why they called off the first launch attempt, which made a lot of people very angry. But thankfully, the second attempt went off fine.
Yeah, that's sad.
Well, it happens.
Yeah.
No, it happens. But you know, the onus is on the rocket, and you know, if it's not safe, then you don't launch. It's just the way it goes.
Makes sense.
Yeah, it does. I mean, I guess that's why Cape Canaveral's in Florida on the coast, and okay, makes sense.
Yep.
All right, our next topic. Are we close to coming up with a grand unifying theory to put together the standard model of the universe in the macro level and the quantum world in the micro level into a theory of everything?
I guess that's back to me. So that's kind of what we're trying to do with this idea of quantum entanglement being what space and time really is. It's always the case. I mean, remember, have some respect for the fact that we only invented the telescope 400 years ago, and like we only came out of caves like 100,000 years ago. You know, I mean, do we understand the nature of reality yet? No, right? Okay, so it's a little hard to say that we're going to come up with something that is the absolute ultimate description of everything when you and I are not really conscious yet. We don't even perceive the universe the way it really is. I mean, you know, you can take an ant and you can try to teach it, you know, quantum mechanics all day, but it's just not going to happen. You know, I mean, an ant is an amazing, incredible, complex product of evolution. But this idea that we've reached a perfect understanding of what the universe is, oh my God, no. I mean, at least we know that's not true. But as far as our physics, our science, our human-based mathematics, the idea that gravity and quantum mechanics don't match, everybody knows it's 100 years old. And Einstein was seminal in both ways. I mean, he was one of the fathers of quantum mechanics and the father of general relativity. And, you know, the problem is that, you know, with general relativity, if you plug in how much mass you have, you know, I've got, you know, 2.4 times the solar mass for this neutron star, it will tell you how much space and time will bend. And sure enough, we look at that in our telescope and it matches exactly. But quantum mechanics says that there's no real absolute answer. It's probabilistic. And Einstein couldn't get gravity to be probabilistic. He couldn't quite figure out how that would work. And so the idea is that maybe we were asking the wrong question all along, that it's not that these two things disagree with each other. It's that we didn't build up the structure of our physics right the first time to make them the same. And this is what this idea of quantum entanglement is. So this idea that quantum entanglement is really what space and time is, and gravity and everything. I mean, the thing that's sort of attracting physicists to this right now is that there's absolutely no problem with gravity and quantum mechanics because they're built up on the foundation of entanglement being both things.
Right.
And so, you know, this idea quantum entanglement is a fairly new phenomenon to actually do in the lab. Like I said, Einstein thought of it. Famously, he called it spooky action at a difference. Yes, spooky action at a distance. But now we're very good at it, just technologically. And so an advance in technology makes you say, well, now we probably should understand the physics behind this, really. And that's where the idea that space and time itself are some sort of emergent properties from this underlying quantum structure. There isn't any conflict anymore, and that's one thing that's attractive to this physics. So but like I said, one of the physicists that I worked with when I was at Caltech, Kip Thorne, you may have heard of. He was one of the gravitational wave people. He wrote an interesting book called Black Holes and Warped Space-Time: Einstein's Outrageous Legacy. That was kind of a good book too. But he said, it may be a little soon to follow the rabbit holes all the way down, because we may not really have gotten to the underlying idea of what the universe is yet.
So the science is not even ready then?
So that doesn't stop us from taking the first step and doing our theoretical physics and saying, maybe it's this, and then seeing, okay, can we do experiments that say, okay, it's definitely not that, so I have some respect for how far we need to go. When people say, what is the power of consciousness? I'm like, we have ample evidence in physics that we are not perceiving reality with the complexity and completeness of what it really is. Like I said, an ant is a fabulous thing, a complex social insect. But it doesn't have the capacity to write, Mozart's symphonies. Right. And I think that we will be in that phase for a while, and maybe it'll even take AI to take us beyond that. But given our current physics, is there something that's emerging that might be a unifying theory, possibly with this idea that space and time doesn't exist? It's all underlying quantum entanglement. And so what do we do with that? I mean, what do the philosophers do with that? What do the poets do with that? When you say there's no such thing as space and time, any idea that anything changes is probably an illusion of this entanglement, good luck.
That's why we write these books.
That's why we write these books. That's right. That's why imagination takes us through that.
Right, because we want to know, maybe it's this way or maybe it's that way.
Yeah, exactly. And so let your imagination, let your fantasy, go, because that's how we start to kind of grapple with these ideas and play with them. And and then eventually, hopefully, there'll be something that we can do an experiment on. We never thought. Einstein never thought that we'd actually discover a black hole, even though his physics predicted it. Einstein never thought that we'd find a neutron star. He predicted that too, but he didn't think we'd actually find it. He never thought that we'd actually experimentally demonstrate quantum entanglement. And then it's like, whoops, okay, we did.
It's great. That's just great. Thank you, Michelle. That's amazing. It's like every time I hear it, it's like another way to get your mind blown, another way.
Yeah.
It goes in all different directions. It's all right. Maybe 11 different dimensions.
Teri, it's your turn.
All righty. So what is the latest that we've learned about black holes since the first image was taken in April 2019 by the Event Horizon Telescope collaboration? Of the supermassive black hole at the center of the M87 galaxy. So that was a really long question there. Yeah, anyway, so what do we know about black holes? It's new.
Anybody else want to take that one? Or
it's all you.
Oh, great. Okay, all right, sure. Okay, the Event Horizon Telescope is absolutely mind-blowing. If you would have asked me 10 years ago if we could have done this, I would have said no. And for those of you that don't know, I'm probably not gonna get the exact number of observatories, but there was something on the order of a dozen observatories around the world. And they all looked at this black hole that is about 150 million light years away. It's in a galaxy called M87. And this is a supermassive black hole that's probably about 5 billion times the mass of the sun. And so it's a big guy. Interestingly enough, in size, the actual size of the event horizon, remember there's no surface to a black hole, but it's the part where the gravity is bent so much you can't get back out. The actual size of that is just about the size of our solar system. So, 5 billion times the mass of our sun crammed into just the volume of our solar system. And what they managed to do, which was just mind-blowing, is that all of the telescopes took a picture of this black hole at the same time. And so they basically did a trick called interferometry. And if you'd like, I can talk about this because this is one of the reasons space and time cannot be the way we perceive it. With an interferometer, people often say if you take two telescopes and you put them far apart, you can use them like binoculars. That's kind of a simple way of putting it. But basically, my husband, my late husband, was one of the leaders in this area. He built interferometers. And if you want to hear us talk a bit about this, there's a podcast I did for NPR. If you look up Hot Tub Physics, Michelle Thaller, you will actually hear us in our hot tub out back. Because I told NPR that we have the best conversations about physics in the hot tub at night over a glass of wine. And so they said, okay, we're going to bring a microphone. And they did. And but anyway, he talks about what this really is, because what this really is a quantum effect, where you've heard of the double slit experiment, perhaps, where you send one photon that can pass through two slits. This is a single photon from this black hole, from the hot gas around it. You can't see anything from inside the event horizon, actually appearing in all, say, 12 telescopes simultaneously. And to do that, you needed to time the wavelength of light as it gets to the Earth. And you need to catch the same photon, the same wavelength emitted from that material in all 12 places at once. And it really does need to be in all 12 places at once.
Oh my God.
One interpretation of interferometry is that you're looking at overlapping multiple realities. You're looking at overlapping realities where the photon was in different places. You pull them together and you have a telescope that thinks it's the size of the Earth. And because that's how far apart these different telescopes were. They were on every part of the Earth. So that's amazing. And it was all done remotely. I mean, these telescopes were not connected with fiber optic wires. I mean, one was in Antarctica, and there was so much data taken because you need to time the light wave coming in that they actually had literally a ton, not figuratively, literally a ton of hard drives, of terabyte hard drives that needed to be all played together and combined for all this data to work. And sure enough, it did. And damn it if they didn't see that maw, that black heart of the black hole where light can't escape. I was flabbergasted.
That was the picture, the red, the image with the red. And
that's
the
right.
black.
Yeah. So if you want to see the best video of what you're actually looking at, there's a guy I think maybe you're familiar with called Derek Muller who has a podcast called Veritasium. So look up Veritasium black hole. And he will take you through exactly what that black thing is, because it's not as simple as just seeing the event horizon. It's something called the shadow of the black hole. And that's because the black hole bends space and time around it. And so you see not only the event horizon itself, but you see the back side of the event horizon. So it's about 1.5 times larger than the event horizon itself. And then you see glowing material around it. And that's basically a disk that could be in any orientation, but space-time is bending the light to you. So it doesn't even matter if the disk is edge on or face on or anything, because around a black hole, all the light is getting bent in every direction. Some of the light is even orbiting. And yeah, orbiting light. And and so if you want to see piece by piece what this really is, Derek's podcast is the best I've seen. So and don't be confused at the beginning when he says, we think that there's going to be the black hole at the middle of our galaxy released, because that was the intent. The Event Horizon Telescope was going to try to do our big black hole first. It's a lot closer than 150 million light years away. But it turned out that the black hole wasn't consistent enough. It was getting brighter and darker. It was kind of flickery, and they weren't able to get as good of an image. They're still working on it. So they did M87 instead. But it is a really nice rundown. So I guess recently, the last thing that they observed in the last few months was they had the measurements of the polarization of the light around the disk, which gives us a sense of what the magnetic fields are like, basically how particles are lined up. They're working on models of the, you'll notice when you see the image that one part of the disk is brighter and one is darker, and that's what we call relativistic boosting of the brightness. So we're trying to figure out some things from light itself being gravitationally boosted, or dragged back, just incredible ideas. But that image, it looks like just like somebody left their coffee cup down and there's a stain.
Right.
It's not a very great image. But what's contained in that image is absolutely astounding. To catch the same particle of light in 12 different places around the Earth, actually record that with data that was combined, and to really see that dark heart where there's no light coming. I'm getting goosebumps now. Seriously, just
yeah.
So Michelle, I've got a technical question about this. So I can easily imagine, putting 12 telescopes on the same spot in the sky and doing cotemporal observations and turning, quote unquote, the virtual data recorder on for as many hours as you like, subject to the orbits, right? So to me, that part is not quite as, I'll say it's not quite as interesting, although there are challenges there too.
It's not co-adding data. It's not that simple.
Well, no, that's what the next part of the question was.
Right.
So you would need to be recording at a rate that was high enough in all 12 of these locations in order to make sure that the photon counts that you were getting were in fact lined up. Is that another part of the challenge?
That's why this was done in the infrared. Actually, it was done very close to microwaves. So the image that you're seeing is not visible light. It's recorded. I forget exactly which wavelength, but it's basically long wavelength infrared. And this technique can be done invisible, but it's only been done so far with visible with things that are actually linked together with fiber optic cables. So you could actually do that way. So yes, the data recording had to be faster than the arrival of the light wave.
Right. So you need to know what the distance was, and you'd need to be at the Nyquist frequency in order to ensure that you really got the photons. And then all of the rest of it is data analysis, right?
So just think about what you said, the distance, right? So as M87 moves overhead during the night, right? So it starts out over here, rises, and it sets, typical sky going overhead at night. So if you have all your telescopes, all the dozen around the world, that means that the light arrives at this one first at the start of the evening, then overhead it arrives at this one first at the start of the evening, and overhead at this one first at the start of the evening. And so the position of M87 is changing. And so you need to know the distance to that star and the difference between one telescope and another on Earth, right? That becomes incredibly important. If you have to catch the same wavefront, that wavefront is going to arrive at light travel delay times that's continuously changing the entire night.
Do we
And
even
so-
have instruments like that? Do we even actually have any instruments that are that fine?
Yes,
That just
because we
blows
did
my
it.
Well, sure, we do, because we have the
that's why I'm
evidence.
like, how in the world?
But I guess the part that I'm still missing, because I just don't quite get it. So I can see how to make use of all of this information after the fact and basically throw out, let's call them bits that are collected that don't align. What do I need to be doing before the fact to plan the recording? That's the part that I still don't quite see.
I'm not sure. I'm not quite sure what the question is. I mean, certainly the whole idea is the timing of the data.
Right.
So what do you mean before?
Well, so when I've collected all the data, I know that I must use all this information in order to do the data analysis properly after the fact. Do I need to understand what these relative distances are as M87 is rising and setting in order to actually control the data acquisition during the observation? And do I have to plan that ahead of time? Or do I just turn the tape recorders on and then I know I have a billion GPUs worth of data analysis to do after I'm done?
In the case
That's
of
the question.
In the case of physically linked interferometers, probably the best one right now is the VLT interferometer. So the Very Large Telescope in Chile, VLT, yeah, I know, Very Large Telescope. The Very Large Telescope interferometer has four telescopes that are set up that can be even moved a little bit into different interferometer positions. They're all on the same mountain, and they're all connected underneath the floor, basically, with these fiber optic cables. The fiber optic cables are controlled by little carts that actually correct for the distance to the star. They actually move. They actually move on little railway cars, but then within that car, there's piezoelectric crystals that move it fractions of an atom at a time. And so these little carts actually correct for the changing distance that the star is as it goes overhead at night. So if you're setting up your experiment with a physically linked interferometer, yes. Then you actually have these carts that correct for the distance. In the case of this, where it was done completely remotely, it's actually all in the data stamping, all in the timing.
So you just give it like one starting point, kind of a data, and then from that data, it knows what to do. Like,
yeah, I mean, basically, you have the equivalent of an atomic clock signature, underlying all the data. So you have time broken down to very, very sensitive levels, and so then you can play the tapes at exactly the same, I don't know, femtosecond or something like that. Yeah.
oh my God.
That is just, you guys have totally, I am so overwhelmed with all this science. My mind is totally blown.
So I mean, that's a little inside baseball, I have to say. I mean, I'm sorry if that lost people, but I mean, I mean, but that's how they do it, right? I mean, think about that. In order to get the same wavefront to appear in these different places, they need to know. It's called coherence. And if they catch different wavefronts, you don't get anything. You don't get any information at all. And I remember my husband watching for this, because what you get is a fringe pattern. You actually get it's actually like a double slit experiment. You get a fringe pattern, and then you take the reverse Fourier transform of it and do all kinds of lovely things. But anyway, but the thing is that you get nothing at all until the telescopes really do catch the same photon in different places.
Oh my God.
That
At
is
different
just
times.
so amazing. And believe it or not, folks, our time's up.
Oh my God.
Yeah,
This was truly mind-blowing.
you guys have totally, that's why we call this mind-blowing science.
Yeah.
So all you science fiction people, I mean, go out and make use of this and show us where your imagination goes and your fantasy goes, because, I mean, people often think that scientists are the ones that don't like science fiction, that we poo-poo it, and they know it's like, oh, that wasn't very accurate. It's like, you guys have no idea. I mean, we don't believe in space and time anymore, so just have at it. And, I mean, the stuff that I don't like is stuff that we know is not realistic, like Armageddon, right? We actually calculated how much energy it would take to split an asteroid the size of Texas, right? As it was entering the Earth's atmosphere.
Yes.
It's like the output of the sun for a year or something like that. So.
And actually the science fiction is what spurred a lot of science fact. If it wasn't for Jules Verne, would we be go to the moon?
Well, we'll probably take a little bit longer.
Yeah, but folks, we are going to have to close the session. So Jeremy, Michelle, Bridget, thank you.
Thank you so much. This is like, as always, it's just like mind-blowing after mind-blowing, and even my cat here has been like crawling all over me going, what's happening here?
Your cat understands all of this. I'm sure the cat's getting it.
And my little guy is, kind of pacing, going, okay, who?
We know the cats know all of
dog.
it. They're just not telling us.
That's right.
But I do want to thank you again. And Bridget, we will be seeing you in about an hour or so when you do your Mars presentation.
That's right.
So I am really looking forward to that. And next up is, I believe, our first session of trivia. Is it not, Teri?
That is correct. It's the red quiz is going to start at 3:30.
Okay. Thank you.
Thank you again. Thank you.
Thank you for having us.
Great.
Bye, everybody.
Amazing,
Thank you.
as always.
Okay. Guys, you might want to mark calendars for next year.
Yes, please. We would love to have you back again if that's okay.
I mean, if we have to, I'll make the session 3 hours. So thank you very much. And fans, we'll see you guys in the next session. Bye.
Bye-bye.
Bye-bye.
Bye.